Hi everyone, welcome at the Innovation Café. Thanks for the people here in the audience and also the people watching at home. For the people that have not been here before, the Innovation Café is a networking event where we share what Eindhoven has to offer in the fields of tech, design and knowledge. We have a speaker every week or more, but most of the time it's one speaker in this field talking a little bit about what they do. Today we have a presentation by Antoine Post from Team CASA, and he's going to tell a little bit about their social sustainable housing.
Yeah.
Right? So without further ado, I want to get to the presentation, and I'll see you a little bit afterwards. Thanks.
Okay, thank you. So yeah, I'm Antoine Post, and thank you very much for being here today to listen to my story. So I'm going to tell you a little about Team CASA, and before I tell you even who we are, I'll start by saying, why did we start? So if you look at the ecological footprint of the Netherlands, and maybe most of the people here would already know this, then Dutch society needs about 3.5, planet Earths to sustain our society. And most of that is carbon. You can see that if you sort of take away like the carbon bit, then you're just above 1 Earth. Then different countries on Earth do a little bit worse or a little bit better, but on average it's pretty close to this for the whole world as well. So we're short 2.5 Earths, which is a bit of a problem because there's only one of them. And then if you look at the construction industry, because well, you already heard, I'm going to be talking about comfortable, affordable, sustainable alternative for Dutch social housing. So talking a little bit about the construction industry. It's not just that 40% of all the waste in this country is produced by the building industry. It's also that all of the CO2 emissions, so all that carbon we were talking about, 40% of that is due to buildings. And if you look at like worldwide, just all of the concrete alone is like 8% of the total CO2 emissions. So building needs changes. And so we started a student team a couple of years ago, and our mission is to accelerate the energy transition in the built environment, to get basically the academic world and the built and the companies to work together on innovating in that field. And what we decided to do is to create a comfortable, affordable and sustainable alternative for Dutch social housing, hence of course the name CASA. So we're a student team. For those not in the know, the student team is a concept where basically at the TUE and other universities in the Netherlands, a bunch of students come together outside of their usual things they need to do for their degree. And I'm going to switch to this one. Yeah, is this better? Okay. Hold on, I'll just switch like this. So the idea is that students outside of their responsibilities for their degree and their ECTS and whatever, they come together and they design stuff. And so you have the solar team Eindhoven, they produce a solar car. And then there's Team CASA, and we produce a sustainable house. But we call ourselves Team CASA not just because we're a bunch of students, and this is just a subset. In total over the past few years we've had more than 100 students involved, but also because we said we'd integrate the academic and the built environment from the company's point of view. So there's a whole bunch of companies that are either partners, big or small sponsors, that have been involved with us over the past few years. And so I'm going to start basically from the very beginning, because the main topic of today is what are the challenges that we had in designing this comfortable, affordable, sustainable alternative for Dutch social housing. And so I want to start from the beginning with what were our considerations, and then what challenges did we have in practice when we actually started building it? Because, well, spoiler alert, we built it. So I'll start with the concept, and it starts with the installations, right? This graph, I think also known for most, but I need to say it, in the Netherlands at least, in the summer months, we have way too much solar energy, either in the form of electricity or heat. And in winter we have not enough of it, and our consumption doesn't match the generation pattern. And this is the essence of the thing we need to solve here. Because existing concepts, what they basically do, you slap some solar panels on the roof, you turn on a heat pump, and this creates a bit of a problem because these solar panels are on and producing electricity in the summer when, well, everyone else's solar panels are also producing energy and no one is using any of it. And then on the other hand, in the winter, everyone is turning on their heat pump to, use electricity to create heat when there is not enough of that electricity available. So you have this big divide, and obviously, then you can say, well, I'll just sell my electricity back in the summer and buy it back in the winter. But obviously, somewhere in between, it had to be stored somewhere. And right now, the electric grid, we don't have infinite storage. So we said, we'll start with an energy roof. We'll have like a roof with solar panels on top, and it generates heat and electricity. I'll show you how in a second. We'll have a seasonal thermal energy storage. It'll store all that heat for a whole year. And we'll connect it all together with a high voltage DC grid. We'll have some demand-driven ventilation, and we'll design a sustainable building envelope around it. And I'm going fast here, and that's also how we went in the beginning, because we looked at what existed in the market, and went and looked at what is available technology-wise, and we thought, oh, this list, wow, that's not so difficult. So 4 or 5 months, and we had this list, and we were like, oh, we're pretty confident we're doing well. Give us like another 12 months, and maybe we've built this thing. Not that easy, I can tell you. So we started with looking for this generation system, right? We needed this roof that generates all this heat and electricity, and we found one pretty quickly. So there's a company, their name is a bit cut off, but they're called SolarTech. And they have this system, which you can see on the right, which is basically like floor heating, but on top of it, instead of a floor, you put a roof. And then solar panels, you lay them out on top, which is a really cool system, because essentially the solar panels, what they do is they convert as much light as they can into electricity, and everything else is converted into heat. And so they absorb that heat into the floor heating pipes below, and we extract that heat and the electricity, and then we turn on a heat pump. So this heat pump is on in the summer, and it generates really hot water, like 80 degrees Celsius, and we store that in like a really hot seasonal storage. 80, yeah, so like scalding hot, yeah. And then the idea is, of course, so in the winter, we can directly use that energy, which is a very small, like aquarium type pump, to just pump it around and heat up the house. So as I said, so you have this PVD solar, so you have electrical and heat energy. You can get fairly efficient solar panels, you can just smack on there. And this is what it looks like in practice. And then this is where the story starts, right? So you put these solar panels on there, you put these pipes there, and in the drawings, you just connect those things together with a line. But in real life, unfortunately, you cannot just have lines connecting things. There's actual cables, and there's, the safety wire and the earth ground and the, oh boy, then you start getting complicated. And also, the roof cannot leak, so you want to sort of attach everything on the roof. And really, this is where, I can already tell you, the main challenges were not coming up with the idea of putting the solar panel and the heat pump working together. It's really about like putting it together in practice. That was real difficult. And so the installer, the first time they saw our drawings, they were like, yeah, this looks makeable, we could do this. And then they arrive in practice, and then it's like, oh wait, this pipe needs to connect to this pipe, and then it gets difficult. Talk about more about that in a second. I also want to show you the seasonal thermal energy storage. So it's really just a really big bottle of water. It's like a bathtub, but really big. It's like 104 cubic meters. And the reason we chose this is because it's simple, right? Because if you don't need to do it complicated, then do it simple. So it's just a big box of water. It's a closed system, so it doesn't start rusting the pipes or break down or anything. And you just make it so big that with a little bit of insulation, it stays hot for 8 to 9 months at a time. So you can heat up this thing, and in the same way that a big cup of tea takes longer to cool down than a small cup of tea, this very big cup of tea takes 9 months to cool down. And so we can extract heat from it during the winter. And you can see here, how it went in the building process. You have some pictures putting that thing in there. And you can see, like, the the picture they show to sell it looks a little bit simpler, because you see all those pipes there, they need to go somewhere. And boy, did our heat pump, that doesn't come with the right connections. So you need to put 6 valves in between. Well, the next one, and this is one of the more complicated ones, is an AC-DC hybrid grid. So AC is alternating current. That's what comes out of your electrical outlets here. This was designed in the 1800s as like the most efficient way of transporting electrical energy, and so that's what all our systems around are built on today. But after, let's say, the digital revolution, we started getting LED lights, and we started having batteries and solar panels and all that stuff. And all that stuff works on direct current. I'm not going to get into details, but it's just, it works in a slightly different way. And the idea in principle is converting between the two types of electrical power. You lose some efficiency. And so we figured, we have solar panels which generate DC. We have DC. Yeah, so solar panels, just like LED, like solar panels and LED lights are like the same, they're just inverted. So an LED uses electricity to generate light, and a solar panel does the exact opposite. It uses that light to generate electricity. But they're both based on DC. And voltage. So the voltage that solar panels generally create is really low voltage, like 24, 48 volts, something like that. But it's not constant. But to transport that voltage, you want to step it up to like 350 or 750 volts, which we do via these. Is there a pointer on this thing? I think there is. Yeah, so these little boxes here, these magic boxes take like the variable voltage from these panels and transform it into 350 fixed voltage, because then you need less thick cables to transport it all through. That also means there's some safety issues, because high voltage DC, also pretty dangerous. And again, so we went online and we started looking for, we want a DC system, wonder where we could get one. And we found these pictures online. This is by Eaton. It looks like they had everything ready. So we figured, we did so well. We just need to buy that, get them to sponsor us a little bit, and then we can put it all together and make something affordable. And the reality was much more complicated. So it turns out that this picture is their plan, and they have the individual components, but very few of these companies even have an idea of how to bunch them all together. Because again, it's the same with piping and wiring. You cannot just put them together. If one of them is 350 volts and the other is 24 volts, things go wrong. And then ideally also, you want some safety features, like if someone touches a live wire, you'd like the power to cut off and not continue being on and frying that poor person. So it turns out that while the idea in principle is not even that difficult, to get it all working in practice, you need like this. This box is 2 meters tall, and like half of the components in there are just because of these, well, I'm not going to call them silly, but because of safety regulations and because things just don't always like match together. And that also means that it gets really complicated very quickly. And then this battery thing, so on the picture, they show like very small batteries. They're much bigger in real life, which also means that you need to sort of place them somewhere. I'll get to that in a second. And then a heat pump. So the heat pump is something interesting, because a heat pump is the integral part, right? That's the breathing, living heart of our building, because it's what makes it possible for us to use all that electricity and heat in the summer. The first thing that's interesting, so a heat pump usually arrives as an AC unit, right? You plug it into the wall and it uses alternating current. But the funny thing is, in reality, what they do is inside this machine, they'll have a small converter, because alternating current runs at like 50 hertz or 60, depending on where you live. But you don't always want your pump to run at that frequency. You want it to run a little bit slower, a little bit faster, some other speed. And so what they do then is they transform that alternating current to DC current and then back to a different frequency to make their pump run at the right speed, which is a bit of a waste of energy, because they end up having an inefficient converter inside the heat pump. So we told these people from the heat pump, listen up, design us a DC heat pump, and then you'd think all you had to do was remove that one converter and just plug DC right into it. Unfortunately, for some reason, this wasn't the case at all, because then the whole control, like internal control of this
box goes totally haywire. In fact, when we very first started, we figured, we can put this whole house on DC. Why bother with AC altogether? Most stuff that we have in the house has a variable frequency. Like if you have like a vacuum cleaner, you can decide how fast it goes. So you're changing the frequency of the pump. So internally it needs to convert to DC. So we figured, let's start with something simple, a washing machine. Washing machines constantly, turn at different speeds. So we need to switch again? No problem. Yeah? Is this one, can you hear me? Yeah? Okay. So we thought, we'll get some washing machines off of Marktplaats. And we'll locate, inside inside that machine, we'll locate where they transform the energy from one to the other. And we'll just stick 350 volts in there, see what happens, and we're sure it'll work. It should work on paper. In practice, unfortunately, again, so the internal controls of these machines are all wired to respond to AC. And so what happened is the machine worked, no problem, but you could never decide which washing cycle you were going to get. So, one time we do a kid cycle, the other time 90 degrees. Very inconvenient. And that's just one of the other challenges that came up. So again, on paper, looking at the schematics, you could just, stick the 350 volts there. But in practice, things are all interconnected in weird special ways and it doesn't work. And so we get to the final list. So we have a really complicated HVAC system, right? We have this energy roof that that generates warm water and electricity. We have the seasonal heat storage, this hybrid AC/DC grid. The demand-driven ventilation. Honestly, that was the easiest part because they sell that as like complete working systems. Thank goodness. And then we have floor and air cooling, but we decided to leave the air cooling out for now because it's way complicated. We're going to work on that later. But that's actually one very important aspect of, it's not really a problem we ran into, but it was just a free bonus that we got when we were designing. So remember that I told you that the energy roof generates warm water in the summer. Well, your house, if you have floor heating, is in the summer generating warm water for you because, well, you pump the water through your floors and your warm room cools down and your floor gets warmer. So we figured, if you're going to have floor heating anyway, which is a great efficient system for low temperature heating, then the floor cooling is for free. Because if it's too warm inside, then don't bother putting all that warm water through your energy roof. Just send water through your floor and use it to cool down your house, because the heat pump is on anyway, so you have free active cooling. Okay, so what the heat pump does is it transfers heat from a warm place to a cold place, right? So it extracts heat from a warm flow and takes the energy out of it and gives that energy to a different side of the heat pump, and that is like the hot side. So it takes energy. So what a heat pump does is you have one side coming in where, let's say, it's like 30 degrees Celsius, right? That's like water coming from the roof or something. And it extracts heat from that. And so to extract heat from it, that flow needs to get colder. So it gets like 10, 15 degrees, right? And then what it does on the other side is it takes warm water in, which is already at maybe 40 degrees Celsius, but it puts that heat into it and makes it into 80 degrees, if you're with me. So, okay, this is going quite technical. But the end result is that you take a low temperature-ish side of flow, you extract heat from it, and you transfer it to a warmer place to make it even warmer. So the seasonal storage starts at like, if it's 40 degrees in the beginning, you can heat it up to 80 degrees, whereas on the other side you have water coming in at 30 degrees and you can cool it down to 15. Essentially it's what your fridge does too, right? It takes energy from the inside, which is at 8 degrees, turns it into 6 degrees and pumps the extra heat out the back. So it's basically just a complicated fridge that you run in reverse. So you were asking about the dew point of the floor cooling. Really, you mix some extra in. So we have the yeah? Yeah? Yeah. Yes, which is why we measure the humidity in the room. Yeah, so the ventilation system actually pulls air from each room individually and measures the humidity inside that pipe. So the air it took outside, it measures the humidity there and then tells you, so the humidity in that room right now is way too high, so the floor cooling cannot get too cold, so you need to adjust it. So yeah, but indeed, that's the other thing, right? On paper, you didn't have to do this. In practice, boy, so the first time we got asked this question, we had no idea. And then we decided, so we need, sensors in the ventilation ducts to measure the humidity. Yeah, we hadn't thought of that like 2 years ago. But then, we gave some presentations and people started asking us difficult questions, and that's how we figured it out. But so this is what our installation core looks like right now. So the bottom floor in our test, we're building a test apartment building of 2 floors, just 3 apartments, 2 small ones upstairs and a big one downstairs. And so you'll see that in a second in the building concept. And so we have this installation core running in the middle. So where's the pointer? So you have like the whole house here. And then in the middle, we've put all the installations. Because you got to go from your roof generation system, you got to go to your heat pump and do something with it and send it to your seasonal storage. And, well, up and down the ventilation goes. And so the bottom floor you can see here, and the top floor you can see here. And it's not even all of it in there. This is just the heating stuff. Like all the electrical components aren't even in there yet. And then, when you see this, you get pretty shocked the first time. Because remember what I said in the beginning, it's supposed to be for social housing, which means like not too expensive. But then luckily, so we came to the conclusion that if you look at all these systems, it's pretty silly to do this separately for each apartment, right? Because right now what they would do when they try to do social housing but more sustainably is they say, well, I'll have one heat pump and just put one in every apartment, and they'll each have their own little generation unit, and then maybe they'll each even have like their own little solar panels and their own little converter system. But that's really a waste, because if you look at these systems, they're just much more efficient if you just make one of them a little bit bigger. And then what you get in return is you can add all this complexity, but since you're sharing it with so many more apartments, so for example, we're doing 3 apartments, but to be honest, this system is big enough that you could run like 6 apartments on this one installation. Well, then, yes, you can have more complexity, but you divide the price by 6. So it gives you a little bit of breathing room to add all these systems. Because here's the thing, right? All the things that I mentioned here are generally sort of things that we can all agree on. Like, yeah, these things are probably necessary for housing in the future to be sustainable. I mean, you can't get around having a heat storage system. I mean, either that or the electrical grid needs to be majorly renovated. You can't go around generating warm water and electricity. So we thought, you know what? We'll make it super complicated, and then we'll try to get some effort out of that, making it so complicated. So, there's like a million little sensors here and things you can control. And we thought, you know what? In traditional housing, you'd simplify the system as much as possible. Since that's not possible, now that we have all these measurements, maybe we can do something with them. And so we realized that one of the things you could do with that is, for example, predictive maintenance. So if you just hang a couple of microphones in this core and look at the temperatures of the pipes, then if your heat pump is not doing very well, then you'll see that it makes more noise, for example. Like it starts rambling, and like a good car mechanic, they can hear from the sound of the engine that something's wrong. I can't. So we figured, instead of having like someone coming into all of these houses and listening, we'll put a microphone there and use these fancy artificial intelligence algorithms and have them figure out like what is normal and what isn't normal. And we'll connect that to like the temperature sensors. So, normally the heat pump is supposed to work in one way, but maybe it works in a slightly different way. The temperatures start changing a little bit. Well, since we're measuring everything, we can use that to start predicting when is it going to break down, when should you send someone over, and prevent extra costs in the maintenance cycle. So you invest a little bit more beforehand in all the complexity, you get back something that's easier cheaper to maintain, hopefully. All right, so I actually have no idea how long I've been talking, but if it gets boring, just call me out. So the building concept. I said before, so when you create all these installation systems, it's really easy to get lost on the fact that actually, but you do need to make sure that your building around it is made to fit into your installations concept. Because, for example, if we were to take traditional concrete flooring and try to put floor heating in there with this system and floor cooling, you'd get a lot of complaints from people, because people will say, yeah, my feet are cold, in the summer, but the rest of me is really warm because this concrete floor absorbs all the heat, but it doesn't mix well with the air. So we said, well, first of all, concrete is a no-go because it's really bad for the environment, and it's really very difficult to reuse in any way. So we'll build with lighter materials, like wood, for example, mainly. And then, this idea of storing the energy in the thermal mass, instead of having all the thermal mass in the walls and in the floors as concrete, we'll store it as water inside our seasonal storage tank, which is, aim it right down here below. And we'll instead build a flexible structure around it that is as light as possible, so that actually when you turn on the heating, unlike traditional floor heating, you'd have to wait like a couple hours at least for the room to get warm. This system would respond a little bit faster, which also means that your floor cooling works a lot more efficiently, because your floor cooling can actually react to the temperature changes in the room. So we started, well, this is a steel structure, which is the main frame. The reason the steel structure is there is mainly because we were afraid when we started this pilot that we'd have to move it around after it was built. But in essence, if you were to take away this steel frame, then you could just build on top of this thing with a wooden structure as well. And then, so we were going through the building process, and the main thing we learned is that for the building itself, like building with wood and building with various materials, the knowledge is there in the market. So for the installations, we find ourselves being called, 10 times a day by various people who are on building sites saying, whoa, guys, you got to help us. Where do we place the sensors now? Where are they? What is it happening? But for the building, like the structural stuff around it, this knowledge is there in the market. It's just that what you need to do to make it into a sustainable and affordable concept is make it repeatable. Because otherwise, if you do a custom building every time, you'll end up making new mistakes every time. So you'll try to learn from the old mistakes, but because the situation is completely different every time, you'll end up making all sorts of new mistakes. And the best way to prevent that is just make something that is repeatable. So you're saying, what you're saying is that the conclusion of my remark would be maybe you should make the same buildings everywhere. I don't think that's necessarily true, but it is good to have fixed concepts that reuse as much of the same ideas every time. Because, so you want sort of mass customization, right? But at the same time, you don't want to have everything completely custom, because then you do run into the problem of, just like cars, right? So everyone can customize their car. There's many different cars out there, but they all many of them share the same frame. That's sort of a smart idea of doing things, because you can prevent, so car manufacturers generally don't custom make each car, and so they don't run into making the same mistakes on each car every time. That's sort of the, like the mass customization route. How to get there is another topic. So what we decided to do with the pilot is also try to create a building method that, besides just this first pilot, would also be repeatable afterwards. And so there you go. So the idea is that if you take the existing pilot and we're just put it next to each other and put them on top of each other, and you get like these blocks that you can sort of play around with and create different geometries, but the basic building blocks are every time the same. So you can create more of a product for housing rather than doing it custom every time for a project. which is especially important, of course, for the installations, because if you make the installations completely different every time, same problem there. You'll run into different mistakes every time. So if you can standardize, that's where you can really get, something nice happening. Like when you buy laptops, generally laptops are, they produce like hundreds of thousands of them, not 10 of them. In the housing industry, sometimes we build 10 houses and we never do that again. Such a pity. Anyway, so the first one is the pilot that we're going to build in Brainport Smart District, which is just over, if you take the train to Helmond, then the first station is Helmond-Brandenvoort. And so they have a big Brainport Smart District planned right there, where they're going to build like 4,000 sustainable houses. And we're building the first one there, so the very first CASA, right? Yes, yeah, that is their intended layout, yeah. So they have like a green center, and then around it they have like a building stuff. And we're just, our little house is like this one over here. But the rest hasn't been built yet. It's cornfields. Actually, I can show you. So this is what we designed on paper. And then, this morning I took a nice picture, fresh one, and this is what it looks like. So you can see the cornfields in the back there. There's no other houses there yet. We're really the very first ones in that area to build. So we're like the guinea pigs for everything. So it's not just that we're doing this pilot where we're trying to get all the installations and the building stuff right. It's also, how do you make sure that, so the seasonal storage tank, right? Do you need like a permit for that or not? That was a good question. And the same for basically everything else. Like you add batteries to this idea. Does that make it fire safe? What type of batteries do you use? So not lithium ion, that's way too dangerous. So we ended up going for batteries that you can put out with water so that the firemen wouldn't have to be afraid of using water when there's a fire in the house. But that was another one of those things, like you can really go off on tangents. Like you start with this idea on paper saying we'll have batteries, we'll have solar panels, we'll have converters in between. And then you start, going down the road of actually building it and designing it. And then, the firemen come by and are like, oh, that doesn't look safe. They have a point. So, yeah, then you got to adapt. Well, this is the basis of it. Yes, exactly. So the cost of the installation is a very good point, and it touches sort of on what I was saying earlier. If you look at this stuff, and including the battery that is over here on the right, this stuff is pretty expensive indeed. So you couldn't build this for social housing just like it is right now. But the key point, as I said, is these installations we put in here now, they are sort of over-designed. And we're going to be testing them, of course, the coming few months to make sure everything works exactly as we designed. But we don't need to build more houses next to it just to test whether they can handle it, because you can do the measurements with all the sensors we have. So if you have energy left over, then you're good to go. But the key important thing really is to say, yes, this stuff is really expensive to place the first time. But as I said, so there's a couple of things that happen when you start getting slightly bigger scales. If you can have this stuff shared by 6 buildings, that already sort of halves the cost, right? Because right now it's for 3 apartments. But if you can run 6 apartments on it, that essentially halves the cost for no extra investments. Well, I mean, the only extra investment is you need like, a couple of the extra dispensers for floor heating, and that's pretty much it. So getting that scale in there is... so if you look at just the material cost, then you're looking at round about 160,000 euros worth of materials in there. Yeah. Yeah. Which again, that's pretty expensive if you were to use this for each house, right? If you divide it by 6, then you get close to something reasonable. It's way more expensive, but it's also a bit silly in some sense to directly compare it to gas, because we can't build with gas anymore. So yeah, it's also more expensive than yeah, exactly. It can change. I think the main thing is that what we're trying to do is combine, so not just look at the cost of installing it right now. Also look at the cost of maintaining it and the fact that it's future-proof. So with a design like this, you are fairly sure that you're immune against governmental changes, right? So maybe in 5 years from now, the government decides, you know what, gas, not so bad after all, let's do that anyway. But you could also have in 5 years from now, the government saying, okay, guys, actually, this overuse of the electric grid, terrible idea, change all your houses and renovate them all to make them less electricity dependent. And one of the values for social housing corporations is not in so much that you're sure that these changes might happen, but that you're immune against them. Because social housing corporations, the way they work is, they put down these buildings and they own them for 40 or 50 years. And, they want to make sure that for those 40 or 50 years, they don't need to, start renovating all of them because, they have hundreds of thousands of houses. And if they need to renovate all of them at the same time, that's really difficult to do and expensive. So for them, sometimes it's worth it investing slightly more beforehand into getting a much more future-proof and easier to maintain concept that doesn't have the risk of being incompatible with rules in the future. Because if you look at some of the houses that are being built today, for example, the ones where you have lots of solar panels on the roof, the whole net metering idea, so saldering in Dutch, if that gets kicked out, in a couple of years from now, solar panels and heat pumps, these installations, depending on how you treat them, would last like 10, 20, 30 years. But we're thinking now in 5 years, we'll get rid of net metering. What do you do afterwards? So what does it need? Essentially, it doesn't need much more than any other system, because while the pipes, there's many more pipes running everywhere, but the basic components are just, pumps and some filters and some, sensors and actuators. And those are not systems that we're not used to. These systems exist, in every big building. You'll have, utility buildings. You'll have installations like this. The main thing there is, as long as you know exactly what's going wrong, then you're okay. Because then you can you can really go straight to the point of what is wrong. But the thing that costs most money in sort of maintenance is when people don't know where it's going wrong. That's really, so if you look at social housing corporations and then, you're at home, your hot water heating is not working. You call the company and say, yeah, my hot water heater is not working. They have no clue what's going wrong. So they'll come, replace some valve, they'll replace a sensor, they'll replace this, they'll replace that. Yeah, you can. So our installer can log into the system remotely and see exactly what is going on. And if a component were to break, you can locate exactly where it's going wrong. Yeah. Are there any questions from the live stream? Any questions or no? Nothing? How long have I been talking? Is it still on time? Yeah. Sorry. Yeah. I mean, I was just. This is the basis of what I wanted to say. I think exactly these questions are the ones, especially when we got them in the beginning, we didn't have the answers to this, right? So we've been developing for 5 years this concept, and we've gone through many iterations, and we thought in the beginning, we could try to keep it as simple as possible. And at some point, we reached a critical moment where we thought, it's just not going to work to keep it that simple, because this stuff is really complicated. I mean, having this DC grid and the seasonal storage, it gets complicated. So then the only way to go is start using that complicatedness and try to get something out of it. So as you were saying, then since you have all these sensors and all this control system, you can log in remotely, then use it to find a way to make it cheaper. In this case, it doesn't make it cheaper beforehand, but it makes it cheaper in maintenance. Because instead of, like what happened in my house, so I had this problem with my gas water heater, nice traditional system, and they came by like 6 times over the course of 6 months, and they replaced something every time, and they never solved the problem until they decided to just replace the whole water heater. So they spent probably more than $1,000 just in trying to find the problem and not locating it, and ended up replacing the whole system. And this happens disappointingly often, and so getting efficiency in there. If you can just have a simple system that tells you this is where the problem is, this component is broken, they can come in, close it, replace it, and off they go. And that is where a lot of money can be saved. Yeah. So you're asking about ceiling heating. In fact, yes, we were planning to try it out as well because this idea came a little bit late. It came like last year. By then it was too late to change the whole building design because it made the building company a little bit angry if we decided to change the whole design. And we're like, oh no. But indeed, in fact, I suspect for the next version, we'd probably go for that instead of the floor heating. Yeah, in fact, so to my surprise, the building company said, you know, that's actually not a bad idea. It's probably cheaper to do ceiling heating systems than floor heating systems. The other thing is that it's people can have whatever flooring they choose, and especially in social housing, but just when you start looking at really bigger projects, you run into problems of people really like, you know, having these big furry mats on the floor, and those really don't vibe well with floor heating system. And then the floor cooling system works a lot more efficiently, as you said, with ceiling cooling. Sorry? Oh, I haven't heard it. Headaches from ceiling heating. I've never heard that one before, so I will look into it because that's really interesting to hear. I've never heard it before. But see, there you go. That's why so the power of the people, right? So we get more information about this. I will look into that. But so back to that part. So indeed, in fact, so our system, one of the things we'd really like to do is, so we went to this roof system. Right now, this hot water line is running from the roof, but you know, the more stuff you need on the roof, this also costs money, you know. So one of the ways you could save a little bit is say, you know, keep the solar panels, but instead of having this all over the roof, if you have a very efficient cooling system, that makes it more comfortable, so it's more enjoyable for the people living there. If you can do it efficiently enough that you can essentially have the whole room just constantly conditioned to the nice temperature that people would like via ceiling cooling, then you can extract enough heat from the rooms to not have to bother with having the full roof covered in this stuff. That would save costs and also be more efficient in terms of cooling the house. And then the best part is, of course, the heating system works less efficiently when it's ceiling heating, but because so the amount of heat, it's not true. Ceiling heating. All right, then, so you're saying ceiling heating is more, all right. I do know that it's not, I always thought that it was not much of a difference because it's mostly, like, the thing that most people think about the first time is that, you know, ceiling heating would be much less efficient because it's hot air that rises. I do know that it's mostly the radiation that is heating you up. Yeah, ideally no, yeah. But at low temperature heating, all right, well, we'll talk about that later. That's very interesting. But yeah, essentially, well, if not too many people get headaches from it, I think the next time we'd be using ceiling heating, yeah. Again, this is one of those things that, you know, you sort of use you try to be, you know, changing everything, but you try to also keep the parts of the design philosophy that are as simple as possible. You try to hold on to those, and you come to the conclusion, sometimes a little bit too late, you know, actually this too, we could have just done it differently. To be honest, I also got to say, like, we do quite a lot of things differently, and it makes a lot of people very nervous. So sometimes I think it's good that we kept, like, you know, floor heating traditionally. Now, it's not a good reason not to do it, which is why we're here, right? But we sure did make them nervous. I mean, the firemen, we made them very nervous. The people at the municipality, they were very nice. I think sometimes also a bit nervous. Because we had some other ideas, like there was a time that we thought, you know, we'll use the seasonal storage. You know, it looks like a pretty strong structure. We thought, you know, we'll put the whole house on that. We'll use that as a foundation. That turned out not to be a good idea. but only because of the little connection pieces that come here. Those end up like sort of sliding along each other, and it wasn't worth designing a whole new system for it. But this system definitely made the people at the construction site very, very nervous, this idea. Luckily for them, we ended up not going through with it. But this idea of the central core, so we have a steel structure in the center with sort of the floors hanging out. The first time our construction engineer saw this, he was like, this is impossible. You cannot do it like this. Of course, a couple of weeks later, he was convinced, like, okay, maybe you can, just not easy. And so we ended up going ahead with it, with the idea being that all of the installations would be prefabbed inside this core, and it would just arrive on buildings and you put it down. Unfortunately, that's something we learned as we went, is that the steel is, looks obvious in hindsight, but it's way too heavy and way too bulky to put installations in it beforehand. So we had to put the steel down, build a house around it, and then still bring all the installations into the house afterwards. So next time, do away with these steel columns for the installations and just use a little wooden box. It's much easier. So, well, we tried. Yeah. Any other questions? Mm-hmm. Yeah, so the question is, do we have a system as a team to keep track of all these things we discover that could be improved or could be changed? Yeah. Okay, so, well, yes, we do. Actually, it's really simple. We have like a Google Sheets. We have like a list. We write these things down, and we try to categorize them a little bit. Like, hey, is this something that we need to look into? Is it something we need to change, or is it just something to be aware of? Is this like a deal breaker? So we try to categorize them a little bit and per system, and try to see next time, for like the CASA 2 that we want to build, how would we deal with it? So we do actually try to keep track of it. The other thing is that for a lot of things, you also just need to you need to sort of have people that stay long enough in the team to be able to transfer this knowledge, because just having it written down, in a single sentence, sometimes that doesn't work, right? Because it's too simple. And so we tried for a while to have really extensive documentation, which is great, except nobody reads it. So we went back to having, so that's one of the bonuses. So we're a part-time team. Our students that are in the team are not in it full-time, which is a downside because, they don't work as much as a full-time person, but the upside is they'll stick around for much longer. So many of the students that are in our team will stick around for, 3 or 4 years, and even if after they're gone, they don't mind to help us out again. So the system we did is we'll write it down in a short way and then pray that we can reach people for more details afterwards. So that continuity is really tricky as a student team. So you touched on something very interesting there. Yeah. Sorry, I didn't understand the question.
Well, I'm looking for a dynamic where you don't have to, you're not always dependent on documentation.
Mm-hmm.
Where people more have models, so if someone leaves a training, then the next one comes in, can take over the role.
Yeah, so you're talking about the challenge of continuity inside the student team, like how do you make sure people take over the roles? It's honestly, like we have all sorts of things that we try to do for it, but it remains like an ongoing challenge as a team, especially because sometimes, you have a student coming in, they work on a piece, and then they leave, and it takes a while before a new student comes in and picks it up again. So we have like ways that we try to deal with that, but in the end, often the human factor is very important, because we, like I said, we try documenting everything. We even have, we have like like, models of how the house works and everything. But in the end, very often it's also that human factor of, but why did you make this decision? It's a tricky thing, honestly. But yeah, you're right. That's sort of a challenge that is always there for us as a student team. Yeah. 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 So model-based systems engineering. I'm just repeating it for the people there. I'm not, yeah. Yeah. Yeah, I'm not going to repeat all that, but we need to have a beer after, and then we... Or I give you the microphone. As yeah. Well, I'd say you can see it right here. So this is in Brainport Smart District. This is where it's built. So over the coming few months, so we were supposed to have it finished by now, but we don't because, well, there's lots of complicated stuff to deal with. So it always takes longer than you expect. But in September, it really should be working. So if you're ever in the neighborhood, come by, because I'm going to be the first one also living in this house. So I get to be the guinea pig too. So in case something isn't working, I'll be around to fix it, I guess. So, if you guys want to come by, I'll, put a cup of coffee there and we can chat. That's it. Yeah. Thank you very much.
Great. Thanks. Thanks, Antoine, for the talk. So, I already mentioned, I think, that we are a weekly event, usually, but today was the last time before we have a summer break. So we will be back on September 2nd with a talk and drinks as well. So for the people at home, thank you for watching. For the people here, thank you. I hope you guys will stay and have a drink with us, and you can continue chatting about everything. And for now on, I wish you a good evening. So thanks. Dankjewel.